Good morning, everyone. Welcome back. I hope that you've had a good week so far. Happy Friday. Today what we're going to be looking at is part B of the photoelectric effect. You could probably do the examples on your own in part B, but I didn't want to load too much on last time. This lesson can be found on page 16 of your current lesson handout. But before we get started here on the actual examples today, I want to take a few minutes and review the photoelectric effect. In words, what happens in the photoelectric effect is that light, and it doesn't have to be visible light, it could be ultraviolet radiation, it could, although it's rare, be infrared radiation, it could be X-ray radiation, but we typically say light. So light is incident on a metal. What that means is you're shining light on the surface of a metal. And the photoelectric effect is when that light is absorbed and electrons are released from the metal. They come flying out of the surface of the metal with kinetic energy. And as I've mentioned a couple of times, that's the principle on which solar cells operate. Those electrons that come out of the metal because of the energy given to them by the light, those electrons have kinetic energy. And that kinetic energy is converted into electrical energy to be used to power electrical devices. In the photoelectric effect, we've learned that each photon in the light is absorbed by a single electron. So it's a one-to-one interaction. Now, right away, that is telling you that the only way to explain the photoelectric effect is to assume that light behaves like a particle. That is to say, to assume that light is quantized. And it's a one-to-one interaction. A single electron will never absorb more than one photon, and one photon can never be absorbed by multiple electrons. The photon, which is just a little bundle of pure electromagnetic energy, was absorbed by the electron, and that means the electron has that energy. The electron will use some of the energy that was given to it by the photon to escape from the metal, and that cost of freedom is what we refer to as the work function of the metal. Any extra energy that's left over is going to be possessed as kinetic energy of the electron once it is outside of the metal. And that's why we say that the photon has to have an energy greater than the work function in order to eject the electron. Because if the photon has less energy than the work function, then the electron will not get enough energy to overcome the work function. That takes us to a very important idea in the photoelectric effect, which is that in order for the photoelectric effect to happen, the frequency of light that you use must be greater than some minimum value. And that minimum value of the frequency is referred to as the threshold frequency. On the left of this diagram, you can see at the bottom that if the photoelectric effect does not occur, it's because the photon frequency is less than the threshold frequency. But the real reason why the photoelectric effect doesn't occur, if the photon frequency is less than the threshold frequency, is that the photon energy is smaller than the work function. If the photoelectric effect is to occur, then the photon energy must be greater than the work function, and the only way that can happen is if the frequency of light that you use is bigger than the threshold frequency. A couple of other things that we looked at. If you increase the brightness of the radiation that's hitting the metal, then you get more electrons. And the reason for this is because a brighter light source has more photons. So when I compare the two diagrams here, we're using the same color or frequency of light, but I have twice as much light striking the metal on the right. And that would mean the light is twice as bright on the right as it is on the left. Since twice as bright means twice as many photons, and since each photon is absorbed by one electron, you're going to get twice as many electrons ejected. The other thing we learned is that if you keep the intensity or the brightness the same, so you have the same number of photons striking the metal, you'll get the same number of electrons ejected. But if you increase the frequency, so we're going from orange light on the left to green light on the right, and green light has a higher frequency. If you go to a higher frequency light, then the electrons will be ejected with more kinetic energy. when the orange photons are absorbed by the electrons use some of the orange photons' energy to escape the metal, and they have something left over. When the electrons absorb green photons, they use the same amount of energy in escaping the metal as they did before, but that means they're going to have more energy left over because green photons have more energy than orange photons. In the case of the green light, each electron was given more energy compared to how much it was given in the case of the orange light. So it has more left over. Okay, let's take a look at the examples for today. Really, the only thing that's different with the two examples we're going to be working on today is the connection of the speed of the ejected electrons to the kinetic energy of the ejected electrons. If you were to go back and look at the examples we worried about on Wednesday, we were only taking it as far as finding the kinetic energy that each electron had when it was outside of the metal. Well, now we're going to go a little bit further and we're going to calculate the speed. What I told you on Wednesday is still very, very important, namely that in the photoelectric effect you are dealing with three energies. The first energy that we can consider is the energy of the photon. Then we have to consider the amount of energy that the electron requires to escape the metal. That's called the work function. And it's those two energies that determine the kinetic energy that an electron has when it's outside of the metal. The kinetic energy that the electron has when it's outside of the metal will be equal to the energy that the photon had, because when the photon was absorbed, it was transferring all of its energy to the electron, minus the work function, which is the energy requirement for the electron to be removed from the metal. So how do we calculate the energy of the photon? Well, we're going to use E equals hc over lambda. And how can we calculate the work function? The formula for the work function, which you were taught last lesson, is W equals hf0. When I do my calculations today, I'm going to decide to work in joules. And the reason for that should become apparent in a few minutes. So how can we calculate the energy of the photon in joules? I guess we're just going to use the formula E equals hc over lambda, where h is 6.63 multiplied by 10 to the negative 34, and it has units of joule seconds. The speed of light, of course, is 3 times 10 to the 8 meters per second. And then we have to divide that by the wavelength in meters, which would be 450 multiplied by 10 to the negative 9 meters. How are we going to calculate the work function? In joules, we're going to take Planck's constant, 6.63, multiplied by 10 to the negative 34 joule seconds, and we're going to multiply by the frequency, which is the threshold frequency. 3.5 multiplied by 10 to the 14 hertz. All right, let's see what we get for the energy of the photon. 6.63 multiplied by 10 to the negative 34, multiplied by the speed of light, and then divided by the wavelength, which was 450 nano means 10 to the negative 9, so times 10 to the negative 9 meters, gives me 4.42 multiplied by 10 to the negative 19 joules. And now I can go ahead and calculate the threshold frequency, which is Planck's constant, 6.63 multiplied by 10 to the negative 34, times the threshold frequency of 3.5 multiplied by 10 to the 14. And this gives me 2.32 multiplied by 10 to the negative 19 joules. Now we're asked to determine the kinetic energy of the ejected electrons, and we know that the kinetic energy of the ejected electrons is found by taking the energy that the photon gave the electron and subtracting the work function. And we're not really using a formula. I know that I do have a formula written down here. I do have this formula written down. Kinetic energy of the electron is E of the photon minus the work function, but that's not a formula that you would find on your formula sheet. What that is an application of the law of conservation of energy. By the way, when you look at the energy of the photon before it's absorbed, it's bigger than the work function, and that means the photoelectric effect is going to occur. So how are we going to determine the kinetic energy? We're just going to find the difference between those two energies. The kinetic energy of the electron, once it escapes the metal, will be equal to the energy that the photon gave it minus the price that has to be paid to remove itself from the metal, also known as the work function. And if we subtract those two numbers, then we are going to get the kinetic energy of the electron. So I'm getting 2.0995 multiplied by 10 to the negative 19. So rounding to three significant figures would be 2.10 multiplied by 10 to the negative 19 joules. That's the first answer to the question, what's the kinetic energy of the ejected electrons? And again, you could have calculated that, and in fact we did examples like this on Wednesday. What's different now is we also want to now determine the speed of the ejected electrons. Well, that's not too difficult of a task, because you already know that kinetic energy is equal to 1/2 times m times speed squared. And if you know the kinetic energy is 2.10 multiplied by 10 to the negative 19 joules, and that's equal to 1/2 times the mass of an electron, which you know, multiplied by the speed squared, really everybody should know how to find the speed there. This is a calculation that we've done dozens of times. You take the kinetic energy, you multiply by 2, you divide by the mass, and then you take the square root. My kinetic energy is right there on my calculator. I can go times 2 divided by the mass of the electron, which is 9.11 times 10 to the negative 31 kilograms. That's probably stuck in your brain, but if not, you can look it up on your formula sheet. Then we have to hit equals before we take the square root to get an answer of 6.79 times 10 to the 5 meters per second. So V equals 6.79 multiplied by 10 to the 5 meters per second. We have two answers. The first one is the kinetic energy of the electrons, which is 2.10 multiplied by 10 to the negative 19 joules. And the second one is their speed, which is 6.79 multiplied by 10 to the 5 meters per second. Now, before we move on to the next example, I need to highlight something for you, and it's that this formula is only good if you use joules. And that's why I said we were going to work in joules in this question. Because I was looking forward and I was seeing that in the end we wanted to know what the speed was, so I knew that we were going to have to use that formula. Now, could you have done all of your work in electron volts? Absolutely. What would have happened is you would have gotten a number of electron volts for both of these energies that I have highlighted in yellow, when you subtracted those electron volt energies to get the energy I've highlighted in the bluish color, you would have got an energy in electron volts. You would have then had to convert the number of electron volts of kinetic energy to joules of kinetic energy before you did this final calculation. But you need to work in joules whenever you use EK equals a half mv squared. Let's take a look at the second example. Light is incident on a surface whose work function is 3 eV and electrons are ejected with a certain speed. What's the energy of a photon in the incident light, and what's the frequency of the photon in the incident light? Remember that in the photoelectric effect, we are dealing with conservation of energy, and there are 3 energies involved. There is the photon energy. There is the energy required for the electron to escape the metal, which is called the work function. And then there is the kinetic energy of the electron, which of course is what you get when you subtract the work function from the photon energy. In this particular case, you are told the work function. It's 3.0 electron volts. We have the speed of the electron, so it's a pretty, I don't want to say trivial, because it's an important calculation, but it's a pretty simple calculation for us to take 1/2 mv squared and get a kinetic energy for the electron. So 0.5 multiplied by the mass of an electron, 9.11 times 10 to the negative 31 kilograms, multiplied by the speed squared. The speed is 1.18 multiplied by 10 to the 6. Don't forget to square it. That's a common mistake. And we're getting an energy here of 6.34 multiplied by 10 to the negative 19 joules. Now we have a compatibility issue here because the work function is given in electron volts and the calculation for the kinetic energy gives us an energy in joules. So we either have to convert the work function to joules or the kinetic energy to EV, and I think it's probably easier to convert the work function to joules. Another thing that we know by looking at our formula sheet is that 1 electron volt is 1.60 times 10 to the negative 19 joules. For many of us, we know then that to convert electron volts to joules means you're going to multiply the EV by 1.6 times 10 to the negative 19. For some people, that's not obvious. So I would always recommend, if you're unsure, to write out a ratio. We can write 1 electron volt over 1.60 multiplied by 10 to the negative 19 joules equals 3 electron volts over x joules. And of course, when you cross multiply here, you can see that you're going to have to multiply 3 by 1.6 times 10 to the negative 19. And we get 4.8 multiplied by 10 to the negative 19. And now you're really going to have to think. Normally, we're working on finding the kinetic energy of the electron from the other 2 energies. Now we have to work backwards. The electron has, when it leaves the metal, this much energy that's kinetic. And it's free. But in order for it to escape the metal, it has to pay this much energy. It has to give up this much energy. So if the electron has 6.34 times 10 to the negative 19 joules when it left, and it had to give up 4.8 before it left, that means it must have had more energy before it left. And the energy of the photon then can be found by adding these 2 energies together. By taking the kinetic energy of the electron and adding the work function. What does that give us for the energy of the photon? We're going to take the work function plus the 6.34 multiplied by 10 to the negative 19, and we get 1.11 multiplied by 10 to the negative 18. Don't forget, that is the energy of a photon. By the way, just to take a little detour for a second, there's another way you could have reasoned out that you had to add those two highlighted energies. And it's to go back to your basic understanding of the photoelectric effect, which is to say, how much kinetic energy will an electron have outside of the metal? It will have the photon energy minus the cost of freedom. And I think that sentence that I've just written down there as an equation makes sense. The kinetic energy is the leftover energy after you take the work function out of the energy of the photon. Well, if you solve this equation for the energy of the photon, then that's going to involve adding the work function to both sides. And when you add the work function to both sides, you're going to be left with the kinetic energy of the electron plus the work function equals the energy of the photon. And that's what we did. We added the kinetic energy, which is highlighted, and the work function to get the energy of the photon. Had you decided to work in electron volts throughout all of this, so you left the work function in EV, but you converted this energy from joules to EV, then you would have gotten an answer in electron volts. The other thing we're asked to find is, I believe, the frequency of the radiation and energy of a photon is equal to HF, which means the frequency will be that energy of the photon that we calculated divided by Planck's constant. Now, since the energy is given in joules, we have to use the 6.63 times 10 to the negative 34. If you had done all of your work in electron volts and you had a number for the photon energy in electron volts, then you would be dividing by the other version of Planck's constant, the 4.14 multiplied by 10 to the negative 15. So what do we get for the frequency? All I have to do is divide my answer by Planck's constant. And I get for a frequency 1.68 times 10 to the 15 hertz. The question asked us to find two things. One was the energy of a photon in the incident light, and we found that. And the other was, what's the frequency of the incident light? And we found that. So again, the photoelectric effect really is summarized best in terms of calculations in this statement here, that the kinetic energy of an electron equals the energy of a photon minus the work function. In fact, I'm going to get rid of this other stuff. The only thing that we've added to this today is the following. The only thing that we've added to this today is that this kinetic energy of the electron is connected to the speed of the electron by 1/2 mv squared. You do have to remember, of course, that when you use the formula E equals 1/2 mv squared, which we did right at the beginning of this question to calculate the kinetic energy of the electron, you have to be working in joules. When you use 1/2 mv squared and get an energy, it will be in joules. When you put an energy into the equation and you want to find the speed, you have to put it in joules. But that's the only addition to the photoelectric effect today. All right, your assignment is number 8, 9, 11, and 12 that are on page 17 of this handout. Once again, happy Friday. I hope you have a fantastic weekend, and we will talk to you soon. Take care.